Session we are going to discuss about an important topic called Z transform. So before going to the Z transform, let us take a look at the comparison of Laplace and Z transforms. So in the previous session we have done a detailed discussion regarding the Laplace transform. So one may wonder why we are taking so many transforms, what is the purpose of these many number of transforms. Now here you can observe Fourier transform, it plays a key role in analyzing and representing discrete time signals and systems, but it does not converge for all signals. But when it comes to continuous systems, Laplace transform is a generalization of the Fourier transform. If you consider discrete systems, Z transform is the generalization of discrete time Fourier transform, and it converges for a broader class of signals. So you may observe the difference between the various transform. You make a comparison among all these transforms, for which kind of systems, which type of transform will be useful. So in Laplace transform, we evaluate the complex sinusoidal representation of a continuous signal, whereas in the Z transform, it is on the complex sinusoidal representation of a discrete time signal. You observe the variation between them. Okay, so this is what the comparison that you can make between various kinds of transforms. Now you may get the relation between DTFT and Z transform. In the previous session we discussed a lot about discrete time Fourier transform. Does there any relation between discrete time Fourier transform and Z transform? We may discuss here. The DTFT provides a frequency domain representation of discrete time signal and LTI discrete time systems. Because of the convergence condition, in many cases, DTFT of a sequence, sometimes it may not exist, thereby making it impossible to make use of such frequency domain characterization in those particular cases. So you may give the generalization of DTFT by the equation. This we did in the previous session, like x of e power j omega is equal to sigma n is equal to minus infinity to infinity. X of n is a discrete sequence multiplied with e power minus j omega n. This may lead to Z transform. Simply you may replace your e power j omega with your z, then you may get the Z transform. So the Z transform may exist for many sequences for which the DTFT does not exist. So though DTFT does not exist, you may have the existence of Z transform. That is the difference. Again, use of Z transform permits simple algebraic manipulations. Now coming to why we need to go for Z transform. As we discussed, Fourier transform does not converge for all sequences, and it is useful to have generalization of Fourier transform. So in analytic problems, Z transform notation is more convenient than the Fourier transform notation, and hence we may prefer Z transform. So what is a Z transform? So the Z transform is the discrete time counterpart of Laplace transform, and it can be used to assess characteristics of discrete time system. X of n is a discrete time signal, so you may assess the characteristic of a discrete time system for which the input is x of n, h of n is your transfer function, and y of n is the output. So for such discrete time systems, the characteristics can be accessed by making use of Z transform. So in terms of impulse response and frequency response, the Z transform can be used to determine solution to the difference equation. So for a difference equation, you may want to find the solution. Then just apply the transform. You may get the solution for a difference equation in a very easier manner. Y of n minus some k into x of n. This is a difference equation. Differential equation, d square y by dx square plus k into dy by dx. That is called differential equation. Difference equation is difference between the output and input variables like y of n and x of n, and differential equation is the derivative. So you have both difference and as well as differential equation. Now let us take the definition of Z transform. If a sequence x of n is given to us, how do you define its Z transform? Its Z transform is represented by x of z given by sigma n is equal to minus infinity to infinity x of n z power minus n, where x of n is a discrete sequence as already we described. Then x of n, how do we get x of n is? X of n is equal to 1 by 2 pi j integral. So it is a closed integral. Observe that there is a closed circle that is represented on the integral. It is a clear indication of it is a closed integral. Capital X of z, where capital X of z is the Z transform of the sequence x of n multiplied with z power n minus 1 dz. So that is what one may easily understand as inverse Z transform, or the sequence x of n is given by this equation. Now let us take an example of a simple Z transform. Suppose we are given a signal a power n, and a power n is defined for n greater than or equal to 0, and x of n is equal to a power n for n greater than or equal to 0, and the value of x of n is simply 0 elsewhere. So how do you write your x of z is as per the definition of Z transform? X of z is equal to sigma n is equal to 0 to infinity a power n z power minus n, a power n multiplied with z power minus n. So where a power n is given as x of n is given as a power n. So you may expand that, substitute the value of n 0, n1, n2 and so on. So you may get this as a geometric progression with the first term being 1 and the common ratio being a z inverse. So one may get the Z transform of this as capital X of Z as 1 by 1 minus a z inverse, which is again given as z by z minus a. So from this we may observe what are poles and zeros. We defined number of times. The roots of the denominator polynomial are the poles. The roots of the numerator polynomial are zeros. Here we have a pole at z is equal to a. We may observe we have a 0. So z is equal to 0. What is the numerator polynomial is z. So equate it to 0. So then you will get the root. So when you make z is equal to 0, you may observe that it is a 0. So 0 is located at z is equal to 0. Okay. So now you may take, we said that Z transform will be useful for us for finding solution to the difference equation and as well as the transfer function. So Z transform we may use to determine the solution to difference equation. Yeah, we are given an input and output relationship of a LTI system, linear time invariant system, which is given by this equation, where your y of n, it represents the output, and you have your x of n as input, and we are given such equation. Then how do you find the solution for such difference equation? Is bring all output terms to one side and the input terms to the other side. So apply the transform. The transform of y of z, y of n is y of z. The transform of y of n minus 1 as z inverse y of z. This we are going to prove anyway, so need not worry about that. Time being, you may understand the transform of y of n minus k. Y of n minus k is z power minus k y of z as the z transform of a given time shifted sequence with k units as z power minus k y of z. Suppose k value is 2, so z power minus k, in place of k you substitute 2 y of z. So you got that. Now take the ratio of output to the input, h of z is equal to y of z by x of z. So you got the transfer function where capital H of z is the transfer function, which is the ratio of output to the input. So you got the solution to the difference equation in a way, in a very easier manner by making use of z transform. Now the general form of any transfer function will be like this. You have a numerator polynomial and you have a denominator polynomial, say nth order. You are having the numerator polynomial varying sigma n is equal to 0 to capital N, b of n z power minus n. In the denominator you are having sigma n is equal to 0 to capital N, a of n z power minus n, where capital N is the polynomial order. Okay, fine. The transfer function when factorized in terms of the roots, you may find as, here you observe, here sigma is there, here pi means it is the product, sigma n is equal to 0 to capital N, 1 minus beta of n z power minus n, and pi, yeah, n is equal to 0 to n, 1 minus alpha of n z power minus n. So the transfer function when it is factorized in terms of the roots, you got h of z like this. Now let us define how to find the inverse z transform. Suppose you have a system with impulse response h of n, for which the inverse z transform, okay, can be obtained by it can be obtained by two methods. One is the partial fraction method, another one is the long division method. So we may discuss those two methods for obtaining inverse z transform. So here we are given h of z as this, and then 1 by 1 plus a into 1 z power minus 1 a of 2 z power minus 2. So you may factorize that. The application of the partial fraction expansion result, you may get h of z as a naught by 1 minus alpha z power minus 1 plus a1 by 1 minus alpha of alpha 2 z power minus 1, z inverse. So you may easily get the inverse z transform. We will discuss in a very detailed manner how to find the inverse z transform of a given function in detail. So time being, what we will go ahead is with evaluating the z transform of standard functions, unit impulse, unit step, okay, unit ramp, and all these functions we will discuss. Suppose we are given x of n is equal to 1 for n greater than 0. Then you may substitute as per the standard definition x of n z power minus n, x of n z power minus n. So x of n is 1 into z power minus n. So you may substitute different values of n. As a result, 1 plus z power minus 1 plus z power minus 2 and so on. It is going to result in a geometric progression kind, a by 1 minus r, 1 by 1 minus z inverse. As a result, you got z by z minus 1, and mod z should be greater than 1. See, unless if the denominator mod of z minus 1 should be greater than 1, so mod z should be greater than 1. And you have a power function x of n is equal to a power n, and n should be greater than or equal to 0. Then you may find your z transform x of n z power minus n. In place of x of n we have a power n. Limits are from 0 to infinity. You may readily get 1 by 1 minus a z inverse or z by z minus a, and mod z should be greater than a is the condition. Similarly, you may obtain the z transform for a function x of n is equal to n, where n greater than or equal to 0 as z inverse by 1 minus z inverse whole square. That can be rewritten as z by z minus 1 whole square, and mod z should be greater than 1. The values of z for which x of z is finite are known as region of convergence. You may try impulse, okay, step, ramp and other functions. Suppose you are given a sequence x of n is equal to a power n, and we discussed the conditions for causality for a given sequence. A sequence is said to be causal. Suppose x of n is given as a causal sequence. When it will be causal, then x of n is 0 for all values of n less than 0. For all values of n less than 0, x of n is 0. Then you will say it as a causal sequence. And hence, here you observe, it is being a causal sequence, x of n is equal to a power n, for n greater than or equal to 0. You observe what was mentioned here. It is a power n for n greater than or equal to 0, and it is 0 for n less than 0. So clearly we mentioned this is a causal sequence. So it is satisfying the condition that the value of x of n becomes 0 for all values of n less than 0. Now you may apply the standard definition of your z transform. Capital X of z is sigma n is equal to 0 to infinity a power n z power minus n. So a z inverse, that may be rewritten as a z inverse whole power n. Just now we obtained that also, 1 by 1 minus a z inverse z by z minus a mod z greater than a. This already we did, but we didn't discuss in causality sense. Now we may say this as a causal sequence if at all x of n has values for n greater than or equal to 0. For an anti-causal sequence, x of n is 0 for n greater than or equal to 0, and it may have value of minus a power n for n less than 0. You observe, for a causal sequence, x of n is 0 for all values of n less than 0. Whereas for an anti-causal system, x of n does exist and it has a value of minus a power n for all values of n less than 0. So that is the major difference. Again, you may obtain the z transform for this one as instead of x of n, you may substitute minus a power n z power minus n minus sigma n is equal to minus infinity to observe the limits also. As it is being a anti-causal sequence, the sequence does exist for all negative values of n. Okay, it is minus a power n for n less than 0. Minus infinity is a value that is less than 0, and minus 1 is a value which is again less than your 0 value. So observe carefully the limits that are given to this sigma or summation. Whereas for causal, you observe what are the limits that we have given here, 0 to infinity, whereas here minus infinity to minus 1. So you may substitute, you may obtain this. So this is of the form a inverse z whole power minus n, and one may get the z transform of this as z by z minus a mod z less than a, whereas here you observe mod z greater than a. Why? Because this is a causal sequence, and the sequence does exist for all the values of n greater than or equal to 0, whereas anti-causal does exist for all the values of n less than 0. That is the major difference between a causal and a anti-causal. The two sequences have same x of z. So yes, you observe they have the same z transform. A power n, x of n is a power n, x of n is equal to minus a power n. Both got the same x of z, that is, both got the same z transform. But are they region of convergence? ROC is the same? No, the ROC is differing definitely. What you can observe in the causal sequence case is mod z greater than a as the ROC, and mod z less than mod a is the ROC in this case. In yesterday's class, we have discussed in all the previous sessions, we discussed what is ROC, definition of ROC, how ROC is defined. Yeah, so the range of values for which the transform converges is called the region of convergence. So the range of values of z for which your z transform x of z converges is called ROC, is region of convergence. The two sequences have same capital X of z, that is z transform, but their ROC is different. Yes, without ROC we cannot uniquely determine the sequence x of n. Generally for causal sequence, the ROC is exterior of the circle, that means outside the circle having a radius a. So radius of the circle, if you take a your region of convergence is outside the circle with radius a, and for anti-causal sequence it is interior of the circle. Now you are given find x of z and ROC for a sequence x of n given by a power n u of n plus beta power n u of minus n minus 1. Then you may readily obtain x of z as by apply the z transform to x of n. Z transform of x of n is capital X of z. This is of the form a power n u of n, and this is also of the form a power n u of minus n minus 1. You may obtain the value of the z transform as beta minus alpha divided by alpha plus beta minus z minus alpha b z inverse, and the region of convergence lies between alpha and beta, alpha less than mod z less than beta. So ROC lies in between alpha and beta in this particular case. So we may obtain the ROCs for various for unit step, for unit impulse. Okay, these time shifted unit step functions. Okay, time shifted impulse functions. You may obtain the z transform. Just now we have seen proved it for delta of n. The z transform is 1. For u of n step function 1 by 1 minus z inverse. For minus u of minus n minus 1, it is 1 by 1 minus z inverse, and ROC is mod z less than 1. U of n, ROC is mod z greater than 1. Delta of n minus m, its z transform is z power minus m. So ROC is, for this particular case, the ROC is all z except 0, that if m greater than 0 or infinity, if the value of all z except 0 or infinity, all values of z will be the region of convergence except 0. When it is except 0 is if the value of m greater than 0, if the value of m greater than 0, for example z power minus 1, z power minus 2. So in all cases m is greater than 0, fine. And suppose if m less than 0, yeah, you have ROC all z except infinity. So that is what the meaning of this region of convergence for a given sequence delta of n minus m, delta of n time shifted by m number of units, for which the z transform is z power minus m. Now you may have z transform pairs like if a power n u of n is given, the z transform of a power n u of n is 1 by 1 minus a z inverse, and ROC is mod z greater than mod a. Similarly, for minus a power n u of minus n minus 1 is again 1 by 1 minus a z inverse. You observe the variation between the two. See, for a power n u of n, the z transform is 1 by 1 minus a z inverse. Even for minus a power n u of minus n minus 1 also, the z transform is 1 by 1 minus a z inverse. So though the two different sequences are having the same z transform, you observe their ROCs are different. Here in this case the ROC is mod z greater than a, whereas in this case the ROC is mod z less than a. And you may take again another z transform pair, n a power n u of n, n a power n u of n, then result is a z inverse divided by 1 minus a z inverse whole square, and the region of convergence can be shown as mod z greater than a. And again another important function is minus n a power n u of minus n minus 1, which can be taken as a z inverse by 1 minus a z inverse whole square, and the ROC is mod z less than a. Again, we may take the some standard trigonometric functions like cosine and sine, cos n omega naught u of n, for which you may show the z transform as 1 minus cos z inverse cos omega naught divided by 1 minus 2 cos omega naught multiplied with z inverse plus z power minus 2. And the ROC region of convergence is mod z greater than 1. Similar, so how do we prove this? Is very simple. You take cos omega naught n as the summation between two exponential terms e power j n omega naught and e power minus j n omega naught. If you add cos n omega naught plus j sin n omega naught plus cos n omega naught minus j sin n omega naught, as a result 2 cos n omega naught divided by 2 and 2 will get cancelled. I will be left with cos n omega naught 2 of n. That's it. So now you have you may take the z transform for e power j omega naught n and e power minus j omega naught n as per the proof that we have seen. This can be written as 1 by 1 minus e power j omega naught multiplied with z inverse exponential term, and 1 minus e power minus j, because of here minus term is there, minus term, because of that minus term in the numerator of the exponential you will get minus e power minus j omega naught z inverse. So you obtain the z transform for cos n omega naught n u of n as this, and ROC mod z greater. Similarly, you may prove for sin n omega naught u of n as sin omega naught multiplied with z inverse. So this is, what is this? This is a numerical value. How do you say sine of a value, an angle? So you may get a constant value kind of thing, 1 minus 2 cos omega naught z inverse plus z power minus 2. And ROC is mod z greater than 1. And you may take a generalized r power n cos omega naught n u of n, as it can be given as 1 minus r cos omega naught multiplied with z inverse divided by 1 minus 2r cos omega naught z power minus 1 plus r square z power minus 2. And ROC mod z is greater than r. You may write that. So the proof for this r power n cos n omega naught is clearly given here, and one may easily write the z transform of r power n cos n omega naught u of n as this. Similarly, for r power n sin n omega naught u of n can be given as r sin omega naught z inverse divided by 1 minus 2r cos omega naught z inverse plus r square z power minus 2, and ROC is mod z greater than r. So you obtained most of the z transform pairs. For a power n, yes, you may obtain it as 1 minus a power n z power minus n divided by 1 minus a z inverse, and ROC region of convergence is mod of z greater than 0. The z transform is most useful when the infinite sum can be expressed in closed form, usually a ratio of two polynomials in z or in z inverse. So x of z is given by p of z by q of z. The value of z for which x of z is 0. The value of z for which, you may write 0. How do you get a 0 is, what is a pole and what is a 0? The roots of the denominator polynomial must be 0 for obtaining pole. So what should you do? Q of z should be equated to 0. So when you equate the denominator to 0, what happens to x of z? It becomes infinity. Am I right? X of z is equal to p of z by q of z. So the roots of q of z are nothing but pole. So to obtain pole, you must substitute q of z is equal to 0. So if the denominator becomes 0, the fractional value capital X of z becomes infinity. That is what you have written. So there is no difficulty in understanding this. You may understand this very easily. Similarly, how one can obtain 0 is equate the numerator polynomial to 0. So numerator polynomial is p of z. You equate it to 0. So if you equate the numerator to 0, so x of z is 0. So that is very clear for us. So no need of any confusion or difficulty. Convolution. So we have proved for all of the properties, whether it is DTFT, whether it is Laplace transform, we have proved convolution in time domain is equal to multiplication in frequency domain. Same here also, the same property. See, convolution of the sequences x of n and h of n, they are in time domain, and their corresponding z transforms. The transform of x of n being x of z, the transform of h of n will be capital H of z. Then convolution in time domain is resulting in multiplication of their z transforms in the frequency domain. That is what one may understand from this one. So you may prove that in a easier manner. Z transform of convolved signals x of n convolved with h of n is z transform of sigma k is equal to minus infinity to infinity x of k h of n minus k as per the definition of convolution. And you may write that as sigma n is equal to minus infinity to infinity. You applied your z transform and equation. As per the z transform, you may consider this entire thing as yeah, x of n. So x of n multiplied with z power minus n. In place of x of n, we have x of k multiplied with h of n minus k multiplied, the whole thing gets multiplied with z power minus n. And one may easily find this as sigma k is equal to minus infinity to infinity, x of k, sigma n is equal to minus infinity to infinity, h of n minus k z power minus n. Change of index on the second sum, m is equal to n minus k, and one may get this z transform of x of n with h of n. We may prove that in an easier manner, x of z multiplied with h of z. That is what one can understand from this entire calculation, entire derivation. You may prove that, yeah, convolution in time domain is equal to multiplication in frequency domain, multiplication of z transforms of x of n and z transform of h of n, which is given by capital X of z and h of z. The ROC is at least the intersection of is at least the intersection of the ROCs of x of n and h of n, but can be a large region if there is a pole or zero cancellation. The system transfer function is completely, it is analogous or much similar to the CT case, continuous time case. So h of n, for which the transform h of z is given by z transform is given, h of z is given by h of z is equal to sigma n is equal to minus infinity to infinity h of n z power minus n. And for causality, what is the required condition? H of n should be 0 for n less than or equal to 0. Implies the ROC must be exterior to the circle, exterior of a circle, and include z is equal to infinity. It will include ROC will be exterior to a circle, and also it includes z is equal to infinity. Similar to the previous case where we discussed about the initial values and final value theorems, here also we will define initial value and final value theorem. The initial value theorem is defined as x of 0 is equal to limit z tends to infinity capital X of z, and you may prove that initial value theorem and as well as final value theorem making use of limit z tends to infinity x of z. You observe the variation between initial value and final value. In both the cases, you observe z tends to infinity is applied for z transformed signal, whereas final value theorem is applied for the sequence x of n itself. You observe. That is the variation. So don't be thinking in both the cases we have taken infinity. No, it is not like that. Z tends to infinity is the case of your initial value. N tends to infinity is the case of final value theorem. So you may be a little bit cautious in identifying the initial value and final value theorem. The initial value theorem x of 0 is given by limit z tends to infinity capital X of z. So it's enough if I find z transform of x of n as capital X of z, and I may apply the limit z tends to infinity and I may get x of 0 value very easily. Similarly, for the final value theorem, limit n tends to infinity x of n is given by limit z tends to 1 z minus 1 into x of z, where x of z is the z transform of a given sequence x of n. So x of z, you may get this as 3z square minus 2z plus 4 divided by z cube minus 2z square plus 1.5z minus 0.5 is given as x of z. So numerator and denominator are there, very easy. Now you do the partial fraction of your denominator polynomial, that may be rewritten as z minus 1 multiplied with z square minus z plus 0.5, 0.5, and you may apply this which theorem we are applying? Final value theorem. in which it is given limit n tends to infinity x of n is given by z minus 1 into x of z. So you just multiply your x of z with z minus 1. In the numerator z minus 1 is there, in the denominator z minus 1 is there. Both gets cancelled and you are left with 3z square minus 2z plus 4 in the numerator. Z square minus z plus 0.5 in the denominator. And you may substitute the value of z as 1. Okay, as for the given equation, it is limit z tends to 1 z minus 1 into x of z. Here in our case also we are able to get the value of z minus 1 x of z, and you may apply limit z tends to 1 z minus 1 x of z is given by this equation, and you may substitute as z is tending to 1, you may substitute the value of z as 1, and you may obtain easily 5 divided by 0.5, 5 divided by 1 by 2, if it comes to the numerator 5 into 2, 10 is the value. So this is where your initial value theorem and final value theorem are very much useful for us. Now we may take a table of common Z transform pair. Suppose sequence given is delta of n, its transform is 1. For us we are given a sequence u of n. What is its Z transform is 1 by 1 minus Z inverse for mod Z greater than 1, whereas for delta of n it is 1 for all Z value. Similarly, minus of u of minus n minus 1, which is 1 by 1 minus Z inverse mod Z less than 1, mod Z less than 1, whereas here it is mod Z greater than 1. Delta of n minus m. So your impulse time shifted by a factor of m, we may prove it as z power minus m for all z except 0. Similarly, a power n minus a power n u of minus n minus 1, we have listed. What is to be clearly observed is what is the value of transform, and it must be associated with region of convergence, otherwise the Z transform becomes incomplete. The reason being, two different functions may have the same Z transform. For example, you observe here a power n u of n minus a power n u of minus n minus 1 has the same 1 by 1 minus a z inverse as the Z transform. But for the a power n u of n case, the region of convergence is mod z greater than a, whereas for the case of minus a power n u of minus n minus 1, it is mod z less than a. So you can observe the difference very easily, that it is based on the region of convergence that you are going to make a distinction between two different signals. Two different signals may have the same Z transform, but their ROCs are going to differ. Same is the case with u of n minus u of minus n minus 1. Here mod Z, the region of convergence is mod Z greater than 1, whereas in this case mod Z less than 1. You observe minus u of minus n minus 1 is also resulting in 1 by 1 minus Z inverse, in which case the ROC is mod Z less than 1. So you got the Z transforms as the same, ROC are different. So we tabulated all whatever the sequences for which we have found we proved the Z transform, we had kept all of them at one place. Given sequence, its corresponding Z transform and the ROC on the rightmost column. So keeping these Z transforms and their ROC, we may solve the problems in an easy manner, provided if we are thorough with the Z transforms of those standard functions. Now, similar to other transforms, we have for the Z transform, we have the properties, various properties are there. For x of n, if the transform is x of z, its ROC is Rx, and similarly for x1 of n, the Z transform is capital X1 of Z, and Rx1 region of convergence is Rx1. Similarly, for X2 of N, you have region of convergence as Rx2. Yeah, so it satisfies the linearity property. The linearity property is given by Ax1 of N plus Bx2 of N. Yeah, it's a transform will also satisfy the same condition like Ax1 of Z plus Bx2 of Z, and your region of convergence is the intersection between x1 and x2. So that is the reason why contains ROC has the intersection between Rx1 and Rx2. Similarly, a time shifted sequence by n naught units, you may find the Z transform as Z power minus n naught x of Z is a discrete sequence x of n multiplied with Z power n, Z naught power n. You may get that as x of Z by Z naught, and mod of Z naught Rx is the region of convergence. Similarly, if I multiply a sequence x of n with n, the resultant will be minus Z d by dz of x of Z. That is the differentiation in the frequency domain or Z domain. Multiplication in discrete sequence, x of n gets multiplied with n. Its corresponding Z transform is minus Z d by dz of x of Z. So x star of n is the given sequence, x star of Z star is the complex conjugate of its, and its region of convergence is Rx. So real part of x of n, imaginary part of x of n. These properties already we have discussed in all the transforms. So here also most of the transform properties hold good for Z transform also. So these are the properties of the Z transform, like time shifting, time scaling, all these we have discussed. Then the important concept, as I told you, we are supposed to find the inverse Z transform for a given sequence. So how do you find? Recall the definition of inverse Laplace transform. So inverse Laplace transform definition, if you recall, x of t, it is a continuous time sequence. X of t is equal to 1 by 2 pi j integral alpha minus j omega, upper limit being j plus alpha plus j omega, x of s e power st ds. So you may write this as 1 by 2 pi j over the closed contour or closed interval x of s e power st ds. So the inverse Z transform follows from this. X of n is equal to 1 by 2 pi j c x of z with z power n minus 1. So evaluation of this integral is beyond the scope, so we are not going to discuss that. Instead, as with the Laplace transform, we will restrict our integral interest in the inverse transform to rational form. So rational, you bring that into the rational form. As we discussed, inverse Z transform can be obtained by just two methods. One method is long division method, another one is the partial fraction method. So we may take two different examples. One example in which x of z is given by z square minus 1 divided by z cube plus 2z plus 4, we may use the method called long division method. So you have taken z cube plus 2z plus 4 here and z square minus 1, and now you may multiply with z power minus 1 as a result. Why should I multiply this with z power minus 1? See, I want to have z square, so how do I get from z cube the z square polynomial? Is just multiply it with z power minus 1. That is what we did, or divide it with 1 by z, or multiply it with z power minus 1. As a result, you will get z square plus 2 plus 4 z inverse. So very easy, and you may subtract this from z square minus 1. So minus z square minus z square 0, minus 1 minus 2, so minus 3, 0 minus 4 z inverse, so minus 3 minus 4 z inverse is the result here. And again you may continue this, 0 into z power minus 2 minus 3 into z power minus 3. So now you may multiply, already you did this with z power minus 1, and then you are now left with 4 z inverse. So from z cube, how can I get this z inverse? Okay, so I should take minus 3 z power minus 3, z power minus 3 into z power plus 3, 3 minus 3, z power 0, 1, but 2z multiplied with minus 3 z power minus 3, 2 into minus 3 is minus 6, z power minus 3 multiplied with z is z power minus 2. So yes, I got minus 6 z power minus 2, minus 12 z power minus 1, and so on. By continuing, you may get the result for your x of z as z inverse plus 0 into z power minus 2, minus 3 into z power minus 3, and so on. So you got the solution for by using a method called long division method. Relatively simple method is your partial fraction method. You are given x of z as z cube plus 1 divided by the same function z cube minus z square minus z minus 2. You take, in this example, the order of the numerator and denominator are the same. That means numerator is third order, denominator is also having the order 3. For this case, we can use a trick, factorizing x of z by z. Instead of factorizing x of z, divide both sides by z. So x of z by z is equal to c0 by z plus c1 by z plus 0.5 plus j 0.86, c1 bar, complement of this is c1 bar divided by z plus 0.5 minus j 0.866. You may write like this. So and also you may take another coefficient c3 divided by z minus 2. So complex conjugate of this is nothing but this one. You may observe that very clearly, and you may now get the values of c0, c1, c2 by substituting the various roots, like roots are the denominator polynomial, roots of the denominator polynomial are called poles. At different pole location you may get the values of c0, c1, and so on, c1, c3. You may get, see if I find c1, c1 complement is complex conjugate of this. Say x plus jy is there, conjugate of that, complex conjugate of that is x minus jy. So you may get those values very easily. And yes, you have written it as x of z is c0 plus c1 z divided by this c1 complement or c1 bar z divided by z plus 0.5 minus j 0.86 plus c3 z by z minus 2. So you may simplify this, making use of your c0. What you did, you divided this numerator and denominator with z. Z by z is 1. So 0.5 plus j 0.866 z inverse. So you may get this x of z like this. See, why you did this effort is we want to bring that into the known form where one can directly write your inverse z transform as c0 is there, c0 delta of n. We want to bring it into the form of like a power n u of n has your transform as z by z minus a or 1 by 1 minus a z inverse kind of thing. 1 by 1 minus a z inverse. That a z inverse in our case being very easy. we may write this in terms of u of n like this. The exponential term can be converted into a single cosine using magnitude or phase conversion. So how do you get a magnitude of a complex number 0.5 plus j 0.866 or 0.5 minus j 0.866 or minus 0.5 plus j 0.866 is square root of real part square plus imaginary part square. You may get that value as 1. Similarly, phase angle you may obtain pi plus tan inverse imaginary part being 0.866 and real part being 0.5. You may get the phase as 4 pi by 3 radians. Similarly, you may find the magnitude for C1, which is magnitude for C1 as square root of 0.429 whole square plus 0.0825 whole square, which can be obtained like this. And similarly, phase angle of this C1, tan inverse imaginary part being 0.0825 and real part being 0.4291, one may get this as 0.19 radians or 10.89 degrees. Now you may comfortably write the equation for x of n as C naught delta of n plus C1 minus 0.5 minus j 0.86 whole power n u of n and so on. So you have what the exercise you did is you tried your level best to bring that to a standard form of a power n u of n, and finally you are able to get the inverse Z transform in a very easier manner. Similarly, you observe whatever we have done, the calculation of C1 and P1 is useful here in x of n case. Okay, so this is a easy problem. Now let us go for the discussion of transfer function. So in addition to our normal transfer function components such as summation, multiplication, we use important additional component called delay. So delay element is represented as D. If I apply x of n as my input, the output is delayed version of the input. So here the output is delayed version of input. Input got delayed by 1 unit is my output. In place of delay element, I may take, as I am discussing about Z transform, the inverse Z inverse is used to represent this delay. So if I apply x of n, my output is the delayed version of x of n by 1 unit. That is what we have shown here. Y of n is equal to x of n minus 1. That is the delayed input x of n by 1 unit. Y of z can be obtained as z inverse x of z. This is often denoted by its z transform. We can illustrate this with an example, assuming all initial conditions as 0. So we are given a transfer function example. Yeah, this is the transfer function example. X of n is here input, and here again to this adder, okay, or to the summation element. Can you tell me what are the two inputs for the first summation element? One input is x of n. Do you observe x of n is input here, and again for the same adder or the summation element, you have another input that is coming. Q2 of n is applied as the input. So result summation of x of n with Q2 of n is resulting in a Q1 of n plus 1. Again, Q1 of n plus 1 is applied as the input for your delay element. Okay, so it is applied for a delay element. Then Q1 of n plus 1 passed through a delay element, and x1 of n is the output of that delay element, and that is applied to an adder, and also that x1 of n is applied to a multiplier, like having a constant 2 as the multiplication factor, and 2x1 of n will be the input for this adder, for which there are two inputs. One is q2 of n is one input, another input is 2x1 of n. Whereas q2 of n plus 1 can be obtained by taking the difference between x1 of n and here, yeah, y of n gets multiplied with this 3y. So 3y of n, this 3y of n gets multiplied again with minus 1. As a result, 3y of n multiplied with minus 1. It is minus 3y of n. So we got it very easy. Minus 3y of n. We got it. So from x1 of n minus 3y of n, x1 of n and 3y of n. So minus 3y of n gets subtracted. As a result, you will get q2 of n plus 1. This is how you can easily understand this. Now you may apply the transform to this. In that case, x of n replaced with x of z. Do you understand? And we have seen q1 of n plus 1. It is an advanced sequence. Yeah, q1 of n minus 1 is delayed by 1 unit. q1 of n plus 1 is a advanced sequence by an advancement of 1 unit. Okay, so q1 of n plus 1 is replaced with z into q1 of z. Similarly, q1 of z is replaced with q1 of n is replaced with q1 of z, and q2 of n plus 1 is replaced with z into q2 of z. And here q2 of z as it is there, y of z is there, and you have here some constant 3 is there, and with this 3 your y of z gets multiplied, and the result here or the output of this block is 3y of z. And one may write the equation of the behavior of the summation nodes. So at this summation node, x of z gets added to q2 of z. Yes, and q2 of z, as a result you got z q1 of z. You have written that z q2 of z. How do you get z q2 of z is here from one direction q1 of z is given input, other direction 3y of z, just now we discussed 3y of z is coming. So difference between q1 of z minus 3y of z is your z q2 of z, that is this one. And similarly y of z is 2 q1 of z plus q2 of z. The three equations are there and three unknowns are there. You may solve the first for q1 of z and substitute in the other two equations. First you try to solve for your q1 of z, that is given by this. Z into q2 of z can be obtained. q2 of z also can be obtained very easily, and you may write your q2 of z as 1 by 1 minus z power minus 2 z x of z into z power minus 2 3 z inverse y of z, and y of z is this equation, and you may simplify that as h of z is y of z by x of z, and you may get it as 2z plus 1 divided by z square plus 3z plus 5 is the solution. Now we are going to discuss the important properties of ROC. So we discussed what is an ROC. The region of convergence is a range of values of z for which your x of z converges is called as the region of convergence. Suppose, what is the first topmost figure A? This figure I am referring, topmost figure. What is it? It is a right-sided signal. Why we are saying right-sided signal is the samples are there only on the right side. Okay, and this we discussed. X of n is a right-sided signal. Does x of n has any values for n less than 0? X of n is 0, right? For n less than 0, and it is having only the samples or the amplitude only for n greater than or equal to 0. We have x of n values, and it is called a right-sided signal. and it has the region of convergence mod z greater than r plus 1. See, we said that it is exterior to the unit circle. Now you observe shaded portion. The shaded portion is ROC, which is exterior, that is outside the circle having the radius r. So outside the circle is having a radius of r plus, say. So 0 to r plus is the radius, and your region of convergence is outside the circle having the radius r plus. Okay, and for this is particularly for a right sided signal. Now let us take another example, an example of a left sided signal in which x of n has samples for n less than 0 and x of n is 0 for n greater than 0. So that means on the right hand side you do not have even a single amplitude or single value for x of n. So x of n is defined only on the left sided, and x of n is 0 for n greater than 0, and x of n does exist for n less than 0. So it is a left sided signal and ROC of the form mod z less than r minus. Similarly, here you have taken a two sided signal. For a two sided means x of n is not equal to 0 for n greater than 0, x of n is not equal to 0 for n less than 0. So for both the cases you have x of n existence. For both the cases means n less than 0 and as well as n greater than 0. So the region of convergence lies in between a circle with a radius of r plus 1 and a circle with radius of r minus 1. In between the two circular in between the two circles you have a ROC, region of convergence here. Here for a left sided signal the ROC is inside the circle with radius r minus 1, right? For a right hand sided signal ROC is outside the circle with r plus 1. So if you remember this, writing the ROC or indicating the ROC becomes very easy for us. Okay, now the continuation of this, just take an example. You are given two poles, 1 by 4 and minus 1 by 2. Okay, a two-sided signal x of n has, for which the ROC is in between the poles. The shaded portion is in between in between 1 by 4 and minus 1 by 2. Can you observe? This is 1 by 4 is the pole that is for the first circle, this 1 by 4. Another pole you have minus 1 by 2. So your ROC is lying between these two poles, in between the two poles. Now take the other case. Right sided signal y of n has ROC outside the circle containing the pole of the largest magnitude. So what is the largest magnitude? You may easily understand. Okay, largest magnitude we are saying, modulus may be taken. So here you have minus 1 by 2 is indicated here and 1 by 4 is indicated here. Both the poles are inside the circle and your ROC is outside the circle. Can you observe here? ROC is outside. Now here ROC is in between the two poles, between minus 1 by 2 and 1 by 4. And again take the same example, left sided signal omega of n or something like that has an ROC inside the circle containing the poles of smallest magnitude. Smallest magnitude is 1 by 4, which is 0.25. 1 by 2 is 0.5. So smallest magnitude is 1 by 4. So the left-sided signal has ROC inside the circle containing the pole of smallest magnitude, the pole of smallest magnitude being 1 by 4. So left-sided ROC is inside the unit circle, and for a right-sided it is exterior to the unit circle, that means outside of the unit circle for a right-sided signal, and for a two-sided signal the ROC lies in between the two poles. That's it. With diagrams and an example, we have a clear discussion about ROC for three different cases of two-sided, right-sided and left-sided. Now, taking a path analogous to that used the development of the Laplace transform, the Z transform of a causal discrete time signal. Causal discrete time signal is given by a alpha power n u of n and mod alpha greater than 0. How do you obtain? As per the definition, capital X of Z, which is Z transform of X of n, is X of n Z power minus n. In place of X of n, we are given what is X of n? A alpha power n, alpha power A, capital A is a amplitude or a constant, alpha power n u of n. So capital A can be brought outside the summation as it is independent of the variation of small n. Capital A, sigma n is equal to minus infinity to infinity alpha power n u of n Z power minus n. That is equal to A into sigma n is equal to 0 to infinity alpha power n Z power minus n. And that may be written as capital A sigma n is equal to 0 to infinity alpha by Z whole power n. Okay, it is the same as alpha power n and 1 by Z power n. See, if it comes to the numerator, it becomes alpha power n Z power minus n. That's it. So for our convenience, we have rewritten this. And the series converges if and only if mod Z greater than alpha. This defines the ROC as the exterior of circle in the Z plane centered at the origin of radius alpha, and the Z transform may be directly given as capital A outside this summation. You may put n as 0. It is alpha by Z whole power 0 plus alpha by Z whole power 1 plus alpha by Z whole square and so on. It is like a geometric progression with 1 plus x square plus x cube and so on up to infinity. So one may write it as a by 1 minus r, where a is the first term, 1 minus r being the common ratio. Common ratio can be calculated as the second term divided by the first term. The first term being 1 divided by 1 minus r is alpha by z. So if you simplify that, you are going to get x of z as a z by z minus alpha and mod z greater than alpha, and this is a causal system and the ROC is outside the circle having the radius of mod alpha. Yes, that is what you have shown in this diagram very clearly. So it is very easy for us to understand. By similar reasoning, the Z transform and the region of convergence of anti-causal, you observe A alpha power n u of n is the causal case, whereas A alpha power minus n u of minus n, you observe u of n is different from u of minus n. U of minus n, u of n is 1 for n greater than 0, whereas u of minus n is 0 for n greater than 0, and u of minus n does exist for negative values, for that is for n less than 0. So you may obtain x of z value as a z inverse by z inverse minus alpha, a z inverse by z inverse minus alpha, the same, and mod z less than 1 by alpha, and this is an anti-causal, and your ROC is given by this, and the circle will be having a radius of 1 by mod alpha. Okay, and you may be asked to find the about the stability of a given system. So you may be given x of n, x of z, obtain the z transform for this, and verify whether the given LTI system is stable or not. If you are given such a problem, you need to understand the condition for stability. We have discussed it many times that the linear time invariant discrete time causal system is stable, bounded input and bounded output. What is BIBO is bounded input, bounded output stable, provided that all poles of the system transfer function lie inside the unit circle in the Z plane. Now the question is, why the unit circle? Why not circle with radius 2? Why not circle with radius 3 or something like that? So now we are going to prove what? The system LTI, the given LTI system is stable, boundary input and boundary output stable, provided that all poles of the system lie inside the unit circle in Z plane. We are going to prove it. Yeah, take binary input and binary output stability. We have mentioned stability of stability a few times so far. So what is it? Consider a system capital H with impulse response h of n. The system is said to be stable in the bounded input and bounded output sense if for every bounded input x there exists a maximum value of n and mod x of n less than infinity. The output is also, see, input should be bounded. So how do we represent input should be bounded? Modulus of x should be less than infinity. Output also bounded. That means mod y should also be less than infinity. That's it. Consequently, Bibo stability happen when mod x less than infinity implies that mod y also less than infinity. It can be shown that a system with transfer function capital H is bounded input and bounded output stable if and only if its impulse response has finite value or finite norm represented by L1, that is sigma n is equal to minus infinity to infinity mod of h of n less than infinity, where h being the impulse response. Now let us try to evaluate the Z transform for this case. So h of n, for which the Z transform is represented as capital H of Z, take that capital H of Z as modulus of sigma n is equal to minus infinity to infinity. Yeah, how do you get the Z transform is h of n z power minus n. In place of x of n, we have h of n z power minus n. And sigma n is equal to minus infinity to infinity h of n z power minus h of z should be less than or equal to, here we have equality, here we have shown less than or equal to, then sigma n is equal to minus infinity to infinity mod of h of n z power minus n, and that is equal to sigma n is equal to minus infinity to infinity mod of h of n. So how we have written this is z power minus n, and n tends to from minus infinity to infinity, and that is replaced where the inequality less than or equal to is due to the triangle inequality, and we imply the fact that mod z power minus n is same as 1 power minus n. As you are aware, e power z is replaced with e power j omega whole power minus n. So that can be replaced with 1 power minus n and is equal to 1. Note, however, that for bounded input and bounded output stable system, the last line in this derivation will be finite 1, and we introduce mod of h of z less than infinity for every z is equal to 1. That is the ROC of a bounded input and bounded output stable system contains the unit circle. So we proved that the ROC of a bounded input and bounded output stable system contains the unit circle. See, with this proof, we never ever forget the important note that ROC of a bounded input and bounded output stable system contains the unit circle, because we proved this important derivation. You will always remember ROC of a bounded input and bounded output stable system contains unit circle. We have seen that causal systems have ROC outside some circle, and so the ROC of a bounded input and bounded output causal system has the form of ROC is equal to is J and mod J greater than R, where 0 less than R less than 1. Similarly, anti-causal system, that means what is anti-causal system? The non-zero h of n is not equal to 0 only for negative time, and h of n becomes 0 for all positive, for negative time, only for negative time, and for all positive values. Have no ROC inside some circle, and so the ROC of a Bibo anti-causal system has the form this mod z less than R, where R is greater than 1. Here you observe mod z greater than R for causal, mod z less than R for anti-causal. So causality and stability, just know the impulse response of a causal system is 0 for n less than 0. For all negative values of n, your h of n becomes 0. Impulse response h of n becomes 0 for negative values of n. That is called a causal system. The impulse response of a causal LTI system is determined from the transfer function by using the right-sided inverse transform. The poles inside the unit circle contribute an exponentially decaying term to the impulse response. The poles outside the unit circle contribute an exponentially increasing term. Now let us take these figures and we will try to find pole and impulse response characteristic of a causal system is shown in this particular figure. For the figure A, this is your figure A. A pole inside the unit circle, you observe an into mark is here. Can you observe that? It is inside the unit circle. A pole, it is inside the unit circle, contributes an exponentially decaying term. You may observe this is an exponentially decaying term to the impulse response, exponentially decaying term to the impulse response. Similarly, a pole outside the unit circle, see, you have taken this as a unit circle, mod z is equal to 1, that is a unit circle, and pole is, where is the pole? Whether it is inside the unit circle or outside the unit circle. For the case B, for the case B, it is clearly indicated the pole is located here, which is outside the circle, unit circle. A pole outside the unit circle contributes an exponentially increasing. So you observe this is an exponentially increasing, whereas the pole inside the unit circle, here it is contributing exponentially decaying term. So two cases, exponentially decaying, another one is exponentially increasing. The first case being exponentially decaying and the second case being exponentially increasing. So you may easily find that. Stable system, the impulse response is absolutely summable and the DTFT of the impulse response exists. The impulse response of a causal LTI system is determined from the transfer function by using right-sided inverse transform. The poles inside the unit circle contribute a right-sided decaying exponential terms. The poles outside the unit circle contribute left-sided decaying exponential to the impulse response. Now you take the case, pole is inside the unit circle, right? The poles contribute a right-sided decaying. So this is a right-sided decaying to the impulse. The poles outside the unit circle contribute a left-sided decaying exponential. See, to the left side you have decaying. That means here at n is equal to 0, high amplitude, n is equal to 1, slightly decreased, n is equal to -2, again decreased, -3, again decreased, and so on. The amplitude is go on decreasing. So you take the two cases here. One is here exponentially increasing on the right side, pole outside the unit circle. Okay, and here again stable system, the impulse response is under DTFT. The impulse response of a causal LTA system is determined by using the function by using right-sided inverse transform. The poles outside the unit circle contribute a left-sided decaying exponential to the impulse response. So you observe exponentially decaying. A pole inside the unit circle contributes to the right side term to the impulse response. A pole outside the unit circle contributes a left-sided term. So here you got left-sided term, whereas here you got a right-sided term to the impulse response. So that is what we have highlighted here. Very easy to understand for us. From the ROC below, region of convergence below, the system is stable because all the poles within the unit circle, stability is decided whether all the poles are within the unit circle or not. And causality can be decided based on right-sided decaying exponential terms in terms of impulse response. Unit circle and poles lying within the unit circle is deciding about stability. Causality is decided based on whether it is a decaying exponential, that too right-sided decaying exponential, then yes, it is causal. So if you are given a system and you are asked to find for both stability and causality, so how do you check for stability and as well as causality? For stability, it can be checked that if the poles are lying inside the unit circle, you may say it is stable. For causality, you may say that if a right-sided decaying exponential impulse response is there, it is a causal system. Okay, so Z-plane and the stability, how do you finally conclude is all the possible values of capital X of Z, that is Z transform, should lie in the Z-plane. For causal sequence, the system is stable if the poles are in the unit circle. So that is what you said. The system is represented by the difference equation. You may take the Z transform of the difference equation. Then the transfer function can be rearranged like this. So why we are discussing this is, if you are asked to implement a discrete time LTI system, you may implement the discrete time LTI system by writing the transfer function like this, h of z, and you may implement that discrete time LTI system. And yeah, just now we discussed how, if you are given a system, a LTI system with a certain transfer function h of z, how do you decide whether it is causal and stable? So what is given? Suppose that the transfer function of an LTI system is given by this equation, h of z. We are asked, can this system be both stable and causal? So you are asked to find out whether that system has both stability and causality. So you need to check for the condition. You take the characteristic equation, that means the denominator polynomial, and you may equate it to 0. So why? Yeah, we just now discussed, if all the poles are lying inside the unit circle, then the system can be said as a stable one. So how do you find the poles of the given transfer function? Is by equating the denominator polynomial to 0. Take the denominator polynomial and equate it to 0. We got the poles at 0.5, z is equal to 0.5, one pole is indicated here, z is equal to 0.8, second pole is indicated. What about the third pole? The pole is located at 1.2. Is the third pole is inside the unit circle? No, it cannot be inside the unit circle, as its location is at 1.2 and it is outside the unit circle. With that fact, one may easily say that the given system is unstable, as one pole z is equal to 1.2 is lying outside the unit circle, and yeah, so you decided about the stability and causality also one can easily identify based on the condition. What condition? For causality we said that right sided decaying exponential. Is it decaying right sided decaying exponential? Then you may say about causality of a system. Suppose if you are given the difference equation like this, and so you may write the transfer function as y of z by x of z as b naught plus b1 z inverse plus b2 z inverse z power minus 2 divided by 1 plus a1 z inverse plus a2 z power minus 2. By taking this term to the right hand side, you will get the transfer function y of z by x of z. Now if you are asked to draw a block diagram for transfer function, you may write in a very easier manner by taking x of z here, by taking y of z here, x of z delayed by 1 unit z inverse. That means I want z inverse x of z as my output. So apply x of z to a delay element z inverse, result is z inverse x of z. Again apply it for another delay element z inverse. What will be the result? Z inverse x of z multiplied with z inverse. So you may get z power minus 2x of z. And you may be having the coefficients like b naught plus b1 z inverse. B naught gets multiplied with 1. b1, whereas b1 should get multiplied with x of z inverse. So where is x of z inverse? So x of z inverse is taken and it gets multiplied with b1 and it is given to an adder. And similarly b2 z power minus 2 x of z is given to an adder. For this adder, what will be the output of this adder is b1 z inverse x of z plus b2 z power minus 2 x of z is the result of this adder. That is given for another adder here which is shown, and b naught is one input, another input is b1 z inverse plus b2 z power minus 2. As a result, we may get the output of this adder as b naught plus b1 z inverse plus b2 z power minus 2 x of z. So simply we got the result on the right hand side, the whatever the numerator polynomial. Similarly, the denominator polynomial can be obtained by applying by taking your y of z and z inverse one delay element, again another z inverse. So taking the coefficients minus a1 and minus a2, taking two summation elements or two adders, you may get this. So we may discuss in detail about the direct form 1 and direct form 2 implementation in the next sessions. Just we are here observing the use of Z transform in easily obtaining these direct form 1 and direct form 2 and how to obtain the transfer function by collapsing two sets of Z inverse blocks. We may do in a detailed analysis in the next sessions. We may do some example problems, realizations in the next session. So time being, just you may understand this is very useful. Now you are given a problem. Which one of the following pole 0 corresponds to the transfer function of an LTI system characterized by an input-output difference equation given by y of n is equal to sigma k is equal to 0 to 3 minus 1 whole power k x of n minus k is given. Minus 1 whole power k x of n minus k, and k varies from 0 to 3. And you are given options A, B, C, and yeah, pole is here kept at the origin, and fourth order pole it is indicated third order pole. Some zeros are indicated on this unit circle, third order pole. In 3 cases it is third order pole, in the 1 case it is fourth order pole. Like that this is given. Now let us try to solve this problem. y of n. How do you get y of n is given by in the equation itself, it is clearly given k is sigma k is equal to 0 to 3 minus 1 whole power k x of n minus k. Now let us try to expand this. Substitute the value of k as 0. Minus 1 whole power 0 is 1. 1 into x of n minus 0. X of n minus 0 is x of n. X of n minus 1. So x of n minus 1 you got minus 1 whole power 1 is minus 1. Minus 1 multiplied with x of n minus 1 is minus x of n minus 1 plus x of n minus 2 and so on. You will get minus x of n minus 3. You got y of n equation clearly. Now you apply the z transform. Z transform of y of n is y of z. Z transform of x of n is x of z. We have just proved z transform of a delayed discrete sequence x of n delayed by 1 unit x of n minus 1. For that z transform is z inverse x of z. For a sequence x of n delayed by 2 units x of n minus 2, it is z power minus 2 x of z. In a general manner, x of n minus k, for which the z transform is z power minus k into x of z. Using that property, we may easily write y of z equation here. And how do you get h of z is ratio of y of z by x of z, and you may take x of z common in all these terms, then take the ratio of y of z by x of z. You may get easily your transfer function h of z as 1 minus z inverse plus z power minus 2 plus z power minus 3 minus z power minus 3. So you may rewrite that as z cube minus z square plus z minus 1 divided by z cube. That is multiplying both numerator and denominator. Denominator is being 1 into z cube. So in the denominator you get z cube. In the numerator you will get z cube multiplied with 1 z cube. Z cube multiplied with z inverse is z square. Z cube multiplied with z power minus 2 z. Z cube multiplied with z power minus 3, it is minus 1. So you may rewrite this as multiplication of z minus 1 with z square plus 1 divided by z cube. And you may do the pole zero plot. See, you have roots of the denominator polynomial are poles. You got z cube in the denominator, so it is very clear it is a third order pole. Fine. And you are now roots of the numerator polynomial. The roots of the numerator polynomial are called zeros. So where are the zeros located? 1. Z minus 1 is equal to 0. Substitute, equate z minus 1 to 0 so that you will get 1 0 which is located at 1. So at 1 you indicate a 0 with this symbol, and z square is equal to plus or minus 1. So you got another 0. Z square is equal to minus 1. So minus 1 can be written as z square is equal to j omega whole square. So z is equal to square root of minus 1. It is imaginary. So you get the zeros on the imaginary axis at 1 and minus 1. Be cautious. Z square is equal to minus 1 means z is equal to square root of minus 1. When z is equal to square root of minus 1, you need to indicate the zeros on the j omega axis instead of on the real axis. So you got that. Now you are given a problem. If x of n is equal to 1 by 3 whole power mod n minus 1 by 2 whole power n u of n, then the ROC of its z transform in the z plane will be. So we are asked about the region of convergence. So you can understand how important it is, the ROC. And z transform we may find for this given x of n. The z transform can be obtained as x of n can be rewritten for our comfort as 1 by 3 whole power n u of n plus 1 by 3 whole power minus n u of minus n minus 1 and minus 1 by 2 whole power n u of n. This entire effort is to bring this to the standard format. You observe as here mod n is given. Can you observe that as mod n is given, we need to rewrite this as 1 by 3 whole power n u of n, 1 by 3 whole power minus n u of minus n minus 1. And see, the first term itself is rewritten in terms of unit step as mod n. The same kind of case we did it in the previous session for Laplace transforms also, if you remember properly. Now, you may take the Z transform on both sides. As a result, Z transform of x of n is x of z. Z transform of a power n u of n is can be obtained as 1 by az whole power n, that may be written as in a simple manner. Similarly, the second term you observe 1 by 3 whole power minus n z power minus n u of minus n minus 1 can be rewritten as 1 by 3 whole power minus n z power minus n. And the third term, yes, sigma n is equal to 0 to infinity 1 by 2 whole power n z power minus n. The reason being u of n is equal to 1 in the range of n is equal to 0 to infinity. You observe that in the third term the limits are replaced with 0 to infinity. Even in the first term also the limits of sigma summation are replaced with 0 to infinity as per the definition of u of n. U of n is non-zero only for the values of n greater than or equal to 0. So u of n does exist for n is equal to 0 to infinity only. So you substitute that n is equal to 0 to infinity 1 by 3 z whole power n sigma m is equal to 1 to infinity 1 by 3 z whole power m minus sigma n is equal to 0 to infinity 1 by 2 z whole power n as the first, second and third terms. As the first series converges, if 1 by mod of 1 by 3z less than 1. Similarly, the second series 1 by 3 z, 1 by 3 or z by 3. Yeah, 1 by 3 z or z by 3. Mod of z by 3 is the second series. Third series is 1 in the numerator. In the denominator, the entire term is 2z. Should be less than 1. So, the series converges if and only if these conditions are satisfied. For the first case, 1 by, in the denominator 3z less than 1. And hence, 1 is less than 3z or 3z is greater than 1 or z is greater than 1 by 3. So, that is what we got for convergence of first series, mod z greater than 1 by 3 condition. For the second series to convert, we got the condition as mod z less than 3. For the third series, we got the condition mod z greater than 1 by 2. And yeah, region of convergence is intersection of this. So, intersection of mod z greater than 1 by 3. Mod z should be less than 3. Mod z greater than 1 by 2. Okay, so ROC will be, now you need to take lowest among 1 by 2 and 1 by 3. The lowest between 1 by 2 and 1 by 3, the highest we have to take. Highest is 1 by 2 is 0.5. 1 by 3 is 0.333. So 0.5 and 0.5 and 0.33. So region of convergence mod x of z will be intersection of above three regions, which is 1 by 2 mod z less than, maximum is 3. Okay, 1 by 2 less than mod z less than 3. Okay, you got it. See, why you have taken 1 by 2 means 0.5 is less than mod z means you are able to get the region of convergence in between 0.5 less than z less than 3. Okay, so this is what you obtained as the ROC. Two systems. Now you are given two systems. One system is having transfer function h1 of z, another system is having transfer function h2 of z. They are connected in cascade as shown below. The overall output y of n is the same as the input x of n with a 1 unit delay. The transfer function of the second system H2 of Z is given and is asked to find. Okay, what you are given is H1 of Z is given as 1 minus 0.54 Z inverse divided by 1 minus 0.6 Z inverse, and you are asked to find this. Now y of n is equal to y of n, the overall output y of n is same as the input x of n with 1 unit delay. So hence your written y of n is equal to x of n minus 1. Input with 1 unit delay is x of n minus 1. Now take the Z transform on both sides. Z transform of y of n is y of z. Z transform of x of n minus 1 is z inverse x of z. Now take the ratio of y of z by x of z, which is nothing but transfer function capital H of z, which is z inverse. And now you are aware H of z is the multiplication of the two transfer functions H1 of z and H2 of z. H of z is H1 of z multiplied with H2 of z. That is equated to z inverse. We are given clearly H1 of z in the problem itself. We are clearly given H1 of z as 1 minus 0.4 z inverse divided by 1 minus 0.6 z inverse multiplied with H2 of z. As a result, you may calculate H2 of z as z inverse multiplied with 1 minus 0.6 z inverse divided by 1 minus 0.4 z inverse, and you may choose the proper answer as B. B is z inverse multiplied in the numerator 1 minus 0.6 z inverse. Denominator term is 1 minus 0.4 z inverse. Now take another important problem. Z transform is given. Range of mod z is between 0 to infinity. Inverse Z transform of x of n. So it is a routine problem, nothing new, no difficulty. Straight away we may apply this, but you have to be very cautious of applying the concept of this. For delta of alpha multiplied with delta of n plus or minus a, the Z transform is alpha z power plus or minus a, and the inverse of that is alpha delta of n plus or minus a. Given that, what is given? X of z is given for us, 5z square. It is of the form, in this case, alpha being 5 and a being plus 2. So alpha z power 2, 5z square. So according to this, it should be like alpha delta. In place of alpha, we have 5. So 5 delta of n plus a. N plus a being 2, so n plus 2, 5 delta of n plus 2. Similarly, 4 z inverse, 4 delta of n minus 1 plus 3 delta of n. So you got the inverse Z transform very easily by applying this particular property which we discussed in the properties case. So you may readily apply that and you may get that. Another problem, the transfer function of a discrete time LTI system is given by this equation. Consider the following statements. First statement, the system is stable and causal for a ROC of mod Z greater than 1 by 2. Second the system is stable but not causal for ROC mod Z less than 1 by 4. The third statement being the system is neither stable nor causal for ROC. So you need to find whether the given system is causal, stable. Two conditions need to be found, and which statements are correct. We have to identify whether both S1 and S2 are true, both S2, S3 or S1, S3, or all the three are true. So we have to find out. h of z is given. So now you apply partial fractions for this. One may obtain h of z by using partial fractions as 1 by 1 minus 1 by 2 z inverse plus 1 by 1 minus 1 by 4 z inverse. For region of convergence, from this condition we may easily observe for ROC mod z should be greater than 1 by 2. So h of n can be obtained 1 by 2 whole power n u of n. This is of the form a power n u of n. You may observe that 1 by 1 minus a z inverse, where a being 1 by 2 here in our case. Similarly 1 by 4 power n u of n, and for n greater than 0. This is when n greater than 0, h of n does exist. That means system is causal. See, for n greater than 0, you have h of n value. For n less than 0, you should not have any h of n values. Yeah, you got that. And you applied this 1 by 1 minus a z inverse is a power n u of n. Thus the system is, since ROC of h of z includes unit circle, so it is stable also. Hence S1, the statement S1, what the statement S1 is, the system is stable and causal for which ROC mod z greater than 1 by 2. So we have taken mod z 1 by greater than 1 by 2 as ROC for this. And you may take for ROC mod z less than 1 by 4. See, you have 3 ROC values. For all the 3 ROC values, you have to check all the 3 ROC values, and based on those ROC, whether the system is stable or not, one may say ROC mod z less than 1 by 4. Your h of n becomes minus of 1 by 2 whole power n u of minus n minus 1, and 1 by 4 power n u of n. And for the case of mod z greater than 1 by 4 and mod z less than 1 by 2, and is the system is causal? No, h of n becomes 0 for n greater than 0. System is not causal. The ROC of h of z does not include unit circle. See, you observe whether the ROC does include the unit circle or not. So it is not stable, and S3 is true. So you may easily identify whether the given system is stable, causal, non-causal. All these can be obtained very easily. Now you are given again another system equation. X of n is the input, 1 by 3 whole power n u of n minus 1 by 2 whole power n u of minus n minus 1. The ROC of Z transform of a discrete sequence, you are asked, you take the Z transform. So x of z is 1 by 3 power n u of n, and that is equal to 1 by 3 whole power n z power minus n, minus sigma n is equal to minus infinity to minus 1, 1 by 2 whole power n z power minus n. Now can you tell me why we have taken the limits for this as 0 to infinity and for this minus infinity to minus 1? Yes, just think for a few seconds, you will get the answer automatically. The reason being, if we observe, first term is u of plus n, that is u of n. Second term u of minus n minus 1. U of minus n minus 1 exists in between the limits of n from minus infinity to minus 1 only, and hence for the second term the sigma limits are taken from n is equal to minus infinity to minus 1, whereas for the first term the limits are taken from 0 to infinity only. So the first term gives 1 by 3 z inverse, 1 by 3 z inverse less than 1. That implies 1 by 3 is less than mod z. That means mod z is greater than 1 by 3 is the first condition. And second term gives mod z less than 1 by 2. First term mod z greater than 1 by 3. Second term is mod z less than 1 by 2. Thus its ROC is the common ROC of both the terms. That is 1 by 3 less than mod z less than 1 by 2 is the ROC. So you may find easily the ROC. System with a transfer function h of z has impulse response h dot defined as h of 2 value is given as 1, h of 3 minus 1, and h of k is equal k is 0 otherwise. So the impulse response has values only at n is equal to 2 and as well as n is equal to 3. For all other values of n or k, h of k or h of n is equal to 0. And you are asked to consider the statements capital H of z, that is nothing but the impulse response of the transfer function in z domain, in frequency domain. H of z is a low pass filter, H of z is a FIR filter. Which of the following is correct? For that, what is to be done? You need to find the z transform of impulse. We have what is given, h of 2 is given as 1, h of 3 is given as minus 1, and otherwise h of k is 0. The diagram of response is given h of 0, 0 only. H of 1 does exist? No, h of 1 is also 0, but h of 2 is 1. So here with a thick line, with bold line we indicated amplitude 1. Similarly, at h of 3 you are having a minus 1 amplitude, that is represented. At all other values h of k may have 0 values. Yeah, it has the finite magnitude value, so it is a finite impulse response filter. See, when do you say infinite impulse response is? If you are having infinite number of samples and infinite number of magnitude values, you may say infinite impulse. But I can clearly observe I am having responses, finite impulse responses, that too only at k is equal to 2 and as well as k is equal to 3. So it is a finite impulse response filter. Thus S2 is true, but it is not a low pass filter. So S1 is false. S1 is false. So option A is correct. Only S2 is true. S2 means H of Z is a FIR filter is true, but H of Z is a low pass filter is false. Low pass filter is it should allow only low frequency signals to pass with some cutoff frequency, so that is not satisfied. So only S2 is true. Yeah, option A is correct. Yeah, you are given a system like this. In the following network, the switch is closed at t is equal to 0 minus 1. That is initial and the sampling starts from t is equal to 0. The sampling frequency is given as 10 hertz. And the diagram 5 volts, there is a switch and there is a 10 microfarad capacitor and a resistor with 200 kilo ohms is there before the sampler itself, and the sampler has frequency 10 hertz, and after the sampler it will go to the Z transform and X of Z. The sample X of n is equal to 0, 1, 2 are given by, we are asked that. The expression and the region of convergence of the Z transform of the sampled signal are. So these are the questions that are being asked. So how do we solve this problem? Okay, this is what. Current through the resistor. One may find current through the resistor easily or not. You may easily find I is equal to I of 0 plus e power minus t by RC. I of 0 plus is V by R. I of 0 plus is V by R. So current is ratio of voltage to the resistance. That is, you may find I is equal to V by R, which is given by voltage is given as 5 volts, resistance is given as 200 K, and this is equal to 25 microamperes, and RC time constant, product of resistance and capacitance is time constant, that is 200 K multiplied with capacitance of 10 micro is 2 seconds. So I is equal to I of 0 plus e power minus t by RC. As per that equation you may write, we got I of 0 plus as 25 microamperes, so 25 microamperes multiplied with e power minus t by RC. E power minus t by RC is 2, so e power minus t by 2, 25 e power minus t by 2 microamperes is equal to, is 5 e power minus t by 2 volts. So I is equal to, how do I get? V is equal to IR, I is equal to V by R, so you may get this value. Here the voltage across the resistor is input to the sampler at frequency of 10 Hz, so you may get X of N as 5 e power in place of e power minus t by 2, okay, t is related to this n as inverse, so here you may write 2 into 10 in the denominator, so you may get this as e power minus 0.05 n for t greater than 0. And for the other problem, X of n is equal to 5 e power minus 0.05 n, U of n is causal signal, its Z transform. Capital X of Z is given by 5 into 1 by 1 minus e power a Z inverse. So here e power a is being 0.05 Z inverse. So you may get this as 5Z by Z minus e power minus 0.5. And its ROC can be computed as this value e of minus 0.05 Z inverse should be greater than 1 and mod Z should be greater than e power minus 0.5. So you may find this value. Another problem is given. The Z transform of capital X of Z of a sequence X of n is given by X of Z is 0.5 divided by 1 minus 2 Z inverse. It is given that the region of convergence of capital X of Z include the unit circle. The value of X of 0 is to be computed. So how do you compute that? What is given? X of Z is given. Since ROC includes unit circle, it is a left-handed system. X of n is given by minus 0.5 2 power minus n u of minus n minus 1, and x of 0 is 0. You apply initial value theorem. X of 0 is limit z tends to infinity. X of z is equal to limit z tends to infinity 0.5 divided by 1 minus 2 z inverse, which is 0.5. That is wrong because here the initial value theorem is not applicable because x of n is defined for n less than 0. So what is the correct option? The value of x of 0 is 0. So though you got 0.5, it is not correct. Okay, since ROC includes unit circle, it is a left-handed side signal, and x of 0 you will get as 0. Applying initial value theorem for this, see, just by seeing x of 0 value, always this type of tricky questions will be asked in the GATE exam. The tricky questions that will be asked is, if you are applying initial value theorem, you may not be able to get, you need to check for the condition. ROC includes unit circle or not, whether it is a left-handed side, left-handed system or a right-handed system. You have to identify and then you have to apply. If the region of convergence of x1 of n plus x2 of n is 1 by 3 mod z less than 2 by 3, then the ROC of x1 of n minus x2 of n include. What is it is to be identified. Okay, so how do you proceed? Here the ROC of addition or subtraction of two functions x1 of n and x2 of n is intersection between the two regions, intersection between R1 and R2. We have been given ROC of addition of two functions and has been asked ROC of subtraction of two functions. Hence, it will be the same. So option D, for x1 of n plus x2 of n, the ROC, whatever the ROC holds good, for x1 of n minus x2 of n also, the same ROC holds good. So this is a very easy question. The region of convergence for the sequence must be, this is ROC is asked for, this is of the form a power n u of n minus b power n u of minus n minus 1. X of n, a power n u of n. x1 of z can be found as 1 by 1 minus a z inverse, where a being 5 by 6. ROC will be calculated as mod z should be greater than 5 by 6. This is of the form x2 of n is minus of a power n u of minus n minus 1. We had done this, proved it as 1 minus 1 by 1 minus a z inverse, where that mod z less than 6 by 5. Thus ROC of x1 of n plus x2 of n is R1 intersection with R2, which is intersection of 5 by 6 and 6 by 5. So mod z is greater than 5 by 6 and less than 6 by 5. The z transform of a system h of z is given by z by z minus 0.2. If the ROC is mod z less than 0.2, then the impulse response of the system is to be found. So h of z is z by z minus 0.2, and you may apply minus a power n u of minus n minus 1, 1 by 1 minus a z inverse, and h of n is minus a power n u of minus n minus 1. So option D is correct. It is straight away very easy question. For z by z minus a, what is the impulse response? So you apply inverse z transform, you may get it as minus a power n u of minus n minus 1 and mod z less than a. If the impulse response of a discrete time system h of n is given by minus 5 power n u of minus n minus 1, then the system function h of z is equal to, you are given 4 options, you need to find this. So the solution can be easily found by making use of the standard Laplace transforms. For minus a power n u of minus n minus 1, the z transform is 1 by 1 minus a z inverse. In our case, in place of a, we have 5 power n u of minus n minus 1. It is 1 by 1 minus 5 z inverse, and which can be rewritten as z by z minus 5. Since ROC is mod z less than 5 and it include unit circle, the system can be found as stable. You may do in an alternate way like this. Yeah, so both are easy for us. Now the ROC of the Z transform of unit step function is given by A, B, C, D option. Option A being mod Z greater than 1, option B mod Z less than 1, real part of Z greater than 0, real part of Z less than 0. H of n is given as U of n. How do you find capital H of Z is sigma n is equal to minus infinity to infinity x of n Z power minus n. And you may find H of Z is convergent if and only if sigma n is equal to 0 to infinity Z inverse whole power n less than infinity. And this is possible when mod of Z inverse less than 1. Thus ROC is mod Z inverse less than 1 or mod Z greater than 1. Very easily one may find the solution for this one. Okay, is it clear? Now you are asked again a standard function, unit step function, the region of convergence of Z transform of unit step function. So how do you find? Unit step is given by U of n. As per the standard definition of Z transform, capital H of Z is sigma n is equal to minus infinity to infinity U of n Z power minus n. U of n is being 1 into Z power minus n. Z inverse whole power n for n is equal to 0 to infinity. H of Z is convergent if and only if this value is less than infinity. And this is possible when Z inverse is less than 1. Thus ROC is mod Z inverse less than 1 or mod Z greater than 1. The Z transform capital f of Z of function f of nt is a power nt is asked. F of nt is a power nt. You may find, making use of standard definition of Z transform, x of n Z power minus n. X of n being a power nt, you may write a power t whole power n Z power minus. This may be rewritten as at Z whole power minus n or at by Z whole power n. That may be readily written as Z by Z minus at. Very easy. So you may observe, if I am thorough with Z transform, from this one may easily score marks. The Z transform of a signal is given by Z inverse multiplied with 1 minus Z power minus 4 divided by 4 into 1 minus Z inverse whole square. Its final value is asked. You need to check whether I can apply the final value theorem or not for this case. Okay, so we are given Z transform. According to the final value theorem, limit n tends to infinity, f of n is same as limit z tends to 1, z minus 1 f of z. So limit z tends to 1, z minus 1 f of s is multiply the given f of z function with z power minus 1. As a result, you are going to get this limit z tends to 1, z power minus 3 by 4 multiplied with z square plus 1 and z plus 1. Substitute z as 1. As a result, you are going to get the value as 1 and option C is correct. So these problems completes the Z transform. Tomorrow we are going to discuss important concepts on discrete Fourier transform and fast Fourier transform. Also please note that for the second phase the classwork will start. The classwork for the second phase gate classes will be scheduled from 26th May to 6th June 2020. So details will be updated in the URL on 23rd May. So you may refer to the website and you may get the update regarding the second phase of classes. I wish you all the best. Once again, I thank all the authorities for giving me this opportunity. I wish you all the best. Thank you.